Hello. So, so I had this question earlier from someone, and here's my attempt at solving it. So we have the volume. We want to find the volume under two planes in the first octant. So this is a basically we're going to use double integrals to find the volume of a space that is bounded by two planes. So there's some things we got to do first. Some things we got to know. So let's take care of some. Here's how we're going to solve it. So say that we have a XY or XYZ axis. So you have you have some curve in 3D space, and it maps to it's above a region on the XY plane. Yeah, right here is a function of x and y, and that's equal to z. And this guy right here is like underneath the function. So this is the bounds of the space underneath. So one of the things we have to know is that if we think of a plane, think of some plane. Say that we have some x is equal to some x naught. So we have a plane, and that could just be this guy right here. This orange guy right here is like some cross-sectional area, and we'll define it as this. It's cross-sectional area of the plane that is in the x. That's in the that's where x is a solid number. It's a plane that intersects the xy plane, but x is not changing. We're calling an area where x is not changing. And it equals to, so it equals to this. And this is a cross-sectional area. And now, here's the idea. In order to solve integrals, or like the volume, you get the volume of this underneath here. And this is important. This is important for this guy right here. So we would know that our dv, because we're going to need to sum all these up in order to have the integral. This is how the integrals work. Our dv is essentially the plane multiplied by some small dx. And this guy right here is our dx. Well, the width is. That is our dx. We may say that the volume is equal to, from A to B, A of x dx. That is our volume. We're summing the slabs, which are the dv's, the slabs. Because I said the dv is defined as what it was. That's our dv. So therefore, I can write the volume as this. This is the volume under f of x of y in 3 space. So I'll show you an example. So we have some 3 space rectangle, and we know z is equal to some c. It's some height z, and the base r is equal to. So it's bounded by this. We have this, and it's bounded, the base, and it's bounded by this. And so we may say, to get our volume, it's just this equation. It's just equal to this, and this is just, this evaluates to that. A way one can think about this is going that we're going to this, we're getting this cross-sectional area right here. So we have it, and we're like, integrating it and we go across the y, so that means we're going from here to here, like we're going from here to here, and that's the area from this boundary in the y to this boundary in the y. That's why we have that here. And we have that A is from this guy right here. That's there. But this is just the x naught is just to show us that this is just one plane. But if we're integrating across x, we go from x naught just to the variable x. So we have this plane, and the plane changes because this f function right here is not a uniform guy. So it changes. And we're integrating. We already got it across the y, which is from here. We got it across the y. Now we want to get it across the x, in this direction. We got it in this direction, and we want to get in this direction. So therefore, we integrate across the dx. So for here, that's what we did. So this is just easy setting it up, just to show you how to set it up. So we got the what we did is we got one side of it. We got this one plane, and we integrate across the y, which is right here. Because this point right here is B. And then to get across the x, we integrate across x, which this guy here is A. So that's how we're doing it. Okay, so I just got to integrate across, integrate from like on the y side, from the y variable, and then integrate across the x variable, and then we have our volume, essentially. Well, here's a way you can think about it. Let's say you have something a little bit more complicated. Okay, so let's say you have something like this. So this is our base and our boundary. So you could just simply think of it as this. So like it's kind of easy. So it's like this guy right here is like our f of x of y. And what we're doing here is basically like our volume is basically equal. We're integrating across like r. Sometimes this is written as d, but right now we're going across r, the base, and we have our function of x of y across some dA. So we have this, and we know our dA. It's from it's going to be the y and the x. We can switch it around, but we switch it around. Okay, so we could switch it around, but we're not going to. We don't have to. So instead of going it from integrating from y to getting across the y first, we could integrate across the x first. But before we do, it doesn't matter. So here's how I'm just going to set this up. Y squared. So now we have our dy, our dx, and our y. Both of them are just from -1 to 1. And there we have it. This is how we set it up, and we got this. So we can just think of it as like some kind of curve over some base. And so once we set it up, we can just plug and chug. So what we're doing is we're integrating like this. So we have this plane here. This is like our A of x, but A of x naught. The reason why it's A of x naught is because it's at this point. It becomes A of x when we're moving it across. We're moving this plane across. It's like we're taking the area of the plane from the y, and then we do the x. So the y first, and then the x. So here's something that's similar to the problem that you're facing. So then we have some tetrahedron S, defined as such. So right here we have as a tetrahedron, and the reason why it's a tetrahedron is because of these boundary conditions right here, which basically means it's like we have a plane that's slanted, but it's in the first octant, and that's what we're interested in. So I'll draw it for you. So we have here is like the tetrahedron, and it's bounded by the xy plane, by the zy plane, and the zx plane. And this right here, this is a slant that's like that's this guy, that's this plane, and I will draw the rest of the plane for you. So what we have here is like the plane that's extending outwards, but it's like bound it by, because we're only interested in the first octant, as said by here. It's the purple is the part that we're interested in. So essentially, all you got to do to find the area of this tetrahedron is simple. It just do what we did before. So we want to find out like what's this? So like what is this and how do we find this? So think of it as like, so this is like our base, and this is like the function or the curve or the plane that is above the base. And that's all. And like with that, we can like, with that idea, we know what to do. So it's like, so how do we like find that? So one way we can think about this is that we have this guy here, the orange plane, which is basically, what we did before, which is a of x naught, and like that's just that goes to our dv, and that's just this guy. So we want to find v is equal to the integral of a of x dx. And so here's how we do it. Draw the xy plane, and let's find our guys that we're dealing with. Let z equal 0. So we have y greater than or less than. So we would have like some so that guy right there is our base. That would be our d. So we can set up the integral. We'd have a of x is equal to 0 bounded by, so 1/2 minus 1/2 of x. And our function, it's like z is equal to a function of x and y. And that would just be 1 minus x minus 2y. So we just write that here. And then we have our dy. And there we go. We got that. So we know that our volume is right here. So we have integrals bounded right here. So I may write this, and our boundaries for the x is 0 to 1. And recall 0 to 1, or x goes from 0 to 1, and our y goes from 0 to whatever this boundary is. And that's why I was able to write these boundaries. 0, that's the y boundary, and there's your x boundary. And this, I already did this. This evaluates to, okay, so that's good. So now, remember, like our d, this guy right here, the purple right here, our d is like our base. It's our base under the curve, and the curve is this plane. Well, in this case, it's this plane. And so we know that this is a solved problem because we can set up the boundaries right here. What about our previous problem? So we have these two planes. We have so what do we do about this? So here's what we do, and it's like this. It's like a tetrahedron as well. So we have a tetrahedron as well, and that's from this tetrahedron is from this guy right here. Like that's the plane that's modeled by here. This plane gives us this part of the tetrahedron, and this is the first octant. So now this guy, so this guy right here, this area of the tetrahedron, this area here, this area, this guy marks that. So here's the deal. Like we have this plane comes from this guy right here. The green plane comes from this guy, and the purple part comes from this guy, this plane. So what we want is we want the area, this lower area right here. We want this area right here. We just want that. We don't want the part in green. We don't want that. So the way we do this is we have our first volume from the tetrahedron. From this guy. This guy gives us the first volume because it's just the base, the D, which would be our D1 of this, the base of this guy, and under this plane, minus the tetrahedron from this green guy, which would be volume 2, and that would be our D2. I'll show you how to get that. I know how to get that out. I'll show you how to get that. And that would just equal our volume, our total our volume that we want. So I'll show you how we do that. So for V1, the way we do that, this guy is our first plane. 2x plus y plus z equal 4. From that, if we set z equals 0, we can see a slope that y depends on x. Y is a function of x. If we set z equal to 0 on the xy plane. And that is just this. And that's what that is. And so our D1 is this. This is like on the xy plane. It's on the bottom of the first tetrahedron, the purple tetrahedron. And so we just need to find, basically we need to integrate the plane curve over this guy. So we can just do that. So that would just be D1 over dy dx. And this guy just comes from, just move all these guys to that side of the equation, and then you have this, because it's our z is equal to 4 minus, so that is our f of xy. And that guy just goes right here. So this is our integral. So we set up the integral. And if I evaluate this integral, I'm going to get 16 over 3. You're free to evaluate this integral yourself. Just take the inner integrand first, and then just take the outer one second, and you'll get 16 over 3. So for V2, we need to find V2, but we need to find D2 as well. So the way we do that is okay. So the thing is that regularly we would find our D, like our area below the curve or the plane, on the XY plane. But for this guy, what we're going to do is we're going to think of the ZY plane as the base. So ZY base. And what we're doing is that we know the curve over that. And the curve is known, and the curve over that is this guy. This is our curve over D2. So let's say I'm going to highlight our D2, and it's right here. It's bounded by this plane, and it's bounded by this guy right here. So we need to find that. So if I were to draw it again, So it's kind of like this. The green, this is our D2. And we can say that this plane right here is basically a function of x is equal to f of y z. That's what we're doing. And we get this from this guy. So we just rearrange it like this. So we just have x is equal to 4 minus y. This is how the curve behaves over the zy plane. And that's what we're doing. So we need to find this guy. So I'll set it up. We'll set it up over dA. So to set this up, we need to see what's actually happening on the zy plane. So we have our y and our z. So this guy right here is the purple guy. The purple this guy. That is the intersection of the zy plane coming from this guy. And this green line right here comes from the intersection of z minus y equal 2. That's where that comes from. That's where that plane comes from. And this plane comes from that. And this plane comes from this. And in this shaded region here is our D2. So now we have D2. So finally, we can set up the integral. To clarify, our y boundary is from 0 to 1. And our z boundary is defined as from 2 plus y, z is greater than that and less than 4 minus y. So here's how we, so this line right here, if we go from this line, if we set our x equal to 0, we can see that we have z is equal to 4 minus y. So that's this guy right here. That's the upper bounds. And the lower bounds is z minus y equal 2. So that's just z is equal to 2 plus y, which is right here. So I'll set up the integral. So here's our integral. So 2 minus 1/2 of y minus 1/2 of z. This is the same as that. And our boundaries is our z boundary, which is right there, and our y boundary is right there. This is our V2. Our V1 minus our volume. So we know that this guy is just 16 over 3 because I evaluated that earlier. This guy, I'll evaluate that right now. All right, so here is V2 as I wrote it out again, and I will evaluate this integral, and that's just, that would be that, 2 over 3y. Shoot. Okay, oh, hang on. This is wrong. And if I evaluate this, okay, so actually this is all wrong. Becomes negative 2y plus 1 plus y squared. And that just becomes 1/3. So here's what we have. So we have V1 minus V2 is equal to 16 over 3 minus 1 over 3. It's just 15 over 3, and that's just 5. And I think that's your answer, dude.